Okay, so I've given you guys a hint by making this a negative b to the power of x, because that's going to make this a little bit different. Now, you'll note that my exponential graph actually has an asymptote. It has an asymptote. They just haven't told us what the asymptote is. But they've also given us some interesting information over here. They've told us that we have a line, a straight line about the point y is equal to x plus 5. That's a very important information that they've given us over there. Right. Now, what do we know about this value of 5? What is 5 exactly? It's a what? In terms of my straight line graph, 5 is the what? It's the Who remembers? The y. Have we already forgotten? That's it, Asante. Good. It's the y-intercept. Correct. It's the y-intercept. And we know that 5 is where our straight line crosses the y-axis, right? Which is here. So what is the value at that point exactly? It's the 0.5. So what is my asymptote of my graph, of my exponential graph? It's at y is equal to positive 5. All right. So that tells us a lot about the Q value. I hope everybody's understanding where the Q value is going then, right? That means Q is going to be positive 5. We're going to end up with f of x is equal to negative b to the power of x plus 5. Now, our next step is to use the other information they've given us. So I'm going to change f of x. I'm going to change f of x to y, because now what I'm going to do is I'm going to take the other coordinate that they've given us, and I'm going to substitute these two values in for x and y, so I can find my b value, right? So this is my x value, 2 is my x value, negative 4 is my y value. So I'm going to go in here and I'm going to replace these two values in here so that I can find the b value, right? So I'm going to have negative 4 is equal to negative b to the power of 2 plus 9, plus 5, sorry, plus 5. And now I'm solving for negative b squared. So I'm going to take positive 5 over to the other side, and that's going to give me negative 5. So minus 4 minus 5 will give us negative 9 is equal to negative b squared. So I'm now going to divide both sides through by negative, so we can get rid of the negative, right? So if I divide both sides by the negative, I'm going to get 9 is equal to b squared. Therefore, b is equal to, what is my value for b, guys? That's it, Asanda, beautiful. B is equal to 3. Okay. All right. And this is just a bit of a challenge based off of what you guys did with Teacher Cat last week. I hope that you guys remember, some of it, Gift. You're going to have to rewatch some of these in order to be okay. Okay. Remember, practice makes progress. So the more we practice, the better we're going to become. All right. Okay, so I'm just going to preface today by saying that we're not going to be doing much of calculating. It's going to be a lot of me talking because we're learning something new, and I want you guys to understand it before we get into all of it, getting together, kind of together. All right, so I want you guys to give me a thumbs up or a thumbs down. Thumbs up if you have started doing trigonometric graphs at school. Thumbs down if you have not and don't even know what I'm talking about. Let me know. Okay, I'm getting one no, one yes, one no, another no. Okay, what about everyone else? Theo says yes. Okay, I just want to see where I need to start this. Well, trigonometric just means trig, like trigonometry, but we're looking at the graphs of trigonometric functions. Okay, because these things are actually graphs, and we're going to talk about that wasn't the question, Gift. Stick to the question. The question was, have you done it? Not did you like it? Unfortunately. All right, okay, let's get into the lesson today. Right, but I'm going to go about it in a roundabout way because I actually want to teach this in a way that makes a lot of sense for us. Right, so we're going to be learning a couple of new words. The first few words over here are going to be this: period, amplitude, vertical shift, and asymptote. Now, if you take physics, you've seen this word and that word before. Yes? Physics peeps, have you seen this before? Yes, we have, right? When we're talking about, price in accounting, correct. When we're talking about waves, if we talk about, I almost said transverse waves. Yes, it is transverse waves, right? Not longitudinal. When we talk about pulses and waves, we are talking about this. Basically, sorry, guys. Oh, I'm trying to switch my heater on, guys. It's cold. It's cold here. Oh. Hi, guys. It's over, guys. It's chai. This weather, it's not the one. Yeah, yes. So when we're talking about the way that sound moves, when we're talking about that kind of thing, we're looking at pulses and waves, right? So if you don't know this, it doesn't matter. It's not going to really. Yes, good, Narisha. If you've never seen it before, it's not really going to affect how you take in today's lesson. But for those of you who do physics, you've got a little bit of an advantage, not much, because I'm going to close the gap for everyone else. All right, so we're going to start by looking at our Cartesian plane, and ma'am's going to draw a circle around our Cartesian plane. There's a particular reason as to why she's doing this, but we're going to talk about it in just a bit. All right. Okay, so I know that on my Cartesian plane, when we're talking about trigonometry, this is 0 degrees. That's 90 degrees. That is 180 degrees. This is 270 degrees. I'm going to put it down here, 270. And if I go full revolution, this becomes 360 again. Now, this we've seen. We're very familiar with this, right? Now, let's say, for instance, I want to draw a triangle. I know, let's say, for instance, I pick that point over there. And I make that point the point 4, 3, right? I know that from the origin, drawing a line to there, I know that I can change this into a triangle by dropping my y coordinate like that, and then doing that. And then I know that the value from here to there is the x coordinate, so that's x, which is equal to 4. And the distance from there to there is y, which is equal to 3, my x and my y values, right? Now, this has a radius r. How am I going to find the radius r, guys? How would I find the radius r? That's it, Narisha. Excellent. We would use Pythag, right? We would use Pythag. Now, here's the problem. Same problem that not Pythagoras, Hipparchus of Nicaea had, right? If we're going to be comparing every single circle that we can draw on a Cartesian plane, all circles are measured differently, right? So what we've decided to do is we've decided that because all of these things like your sine, your cos, and your tan are all ratios, because they are all ratios, what we're going to do at any given point on our graph, we're going to make this a radius of 1. Not necessarily that the point is 4, 3. It definitely is not. Okay, we're going to give every single radius on this circle a radius of 1. Okay, so my r would equal 1. What if I drew this over here? What is the distance of r over here? 1, correct. Narisha, I just need to double check with you that y that you've put there. Is that a question or was that a mistake? I just need to see if we're understanding why we're doing that. Oh, okay. A question why. All right. Remember, Narisha, when we started Trig, I know it was a long time ago, so I'm going to try and refresh your memory. Right. I told you guys that if we have a triangle, right, and the triangle looks this small. If my triangle is this small, if this side is 4 and this side is 3 and this side is 5, my triangle has a certain area or a certain angle, theta. Right. Now, if I take this exact same triangle and I make it even bigger, if I make it even bigger, so I make the distance from there to there 8, and I make the distance from there to there 6, then the distance, what is the distance from here to here then going to be? The distance from there to there is going to be? It's going to be 10. Correct. And how do we know this? Because we know that the bigger triangle is in ratio to the smaller triangle. Okay, thumbs up. Everybody understanding why ma'am can say that? That the bigger triangle and the smaller triangle are almost, they're similar triangles. Agreed? They are similar. So they will be in proportion. We've done this before. They're in proportion. Now, in order for us to establish any sort of ratio from the beginning, if we want to establish a ratio in sine and in cos and in tan, and we want a measurable ratio, one that will work if we multiply it however many times we want, it's easiest for us to use 1. It would just be easiest for us to use a hypotenuse of 1. Okay. Then if we decide to extend this and make that times 3, every other side will just be times 3. So the idea of the ratio of 1 makes everything else simpler, so that when you multiply out the ratio, you can just multiply all the other sides. Am I making sense, Narisha? Okay, lovely. So if I use a radius of 1, right, and I find that if I draw this over here, and I find that this side over here is like, let's say 0, 3, and this side over here is 0, I'm making this up, 0, 4. I'm definitely making it up. It's not correct, right? If my circle has a radius of 1, if I then decide to draw a circle with a radius of 2, if my radius is 2, right? If the radius of the purple circle is 2, then all I need to do to find this side is just go times 2. And this side over here, times 2. Okay. Making sense? Right. The ratio of 1 just makes it easier for us to multiply out when we look for the ratio of any other one. Okay. Because then we'll just double, or we'll just multiply by whatever value, or we can also divide by whatever value, because that value would be valid on all sides. Okay. And it just makes it easier for us to remember the ratio of each of the sides. Okay, cool. All right, so I know this. Now, here's the problem that I'm also going to have. Because at every given point on my circle, the radius is 1, I can create multiple triangles, but every single triangle is going to have a different angle. Right, so I can draw a triangle, a very tiny one, and my theta is going to be equal to 1 degree. And then I can draw another one for 2 degrees, and another one for 3 degrees, and another one for 4 degrees, 5 degrees. No. Now, here's the problem again. In between here, there's also a theta of 0,5 degrees. And inside there, a theta of 0,2 degrees, and a theta of 0,7 degrees. So basically, there are an infinite number of thetas inside here, because I can go to 110,003 degrees. That must give me an answer. But 110,004 should also give me an answer. And 220,442, that must also give me an answer. So if I had to draw all of these triangles, it would also be, it would almost be like me just coloring in the whole thing with triangles. Am I making sense? Thumbs up. Is everyone with me? If I had to draw triangles everywhere, I could draw them at every single degree, which is kind of, it's too much. And we won't be able to see anything. And it will just make it more difficult for us to actually understand what's happening, right? So instead of us drawing every single triangle with a radius of 1 around our circle, what we're going to do is we're going to take our degrees, and instead of drawing them like that, we're going to take them and we're going to draw them out as a straight line. And that's going to give us every single value on a straight line. And thus comes the graph of sine, cos, and tan. So if you look at this graph, I've taken my 0 degrees and I've put it over here. And I've taken that string that made that 360, that made that ratio of 1 or that radius of 1 around, and I've stretched it out across a 360 that lies flat. Instead of in a circle, I've taken that 360 and I've laid it flat. And now I can see every triangle. I'm just going to have to draw every triangle in this direction, which is a little bit easier, because that makes it a little bit easier for me to see. Okay, thumbs up. Are you guys with me? Is you guys understanding what ma'am is saying here? I hope we're all good, right? Lovely. And now we can see everything, which makes it so nice for us, because now we can understand what we're looking at. All right, Vukosi, if you're still not understanding what ma'am is saying, please ask a question. I'm more than happy to re-explain. You just need to explain to me where I lost you, and I will go right back and start again. Okay. Okay. While Vukosi thinks about it, and I'm sure he'll get back to us in just a little bit, we're going to be learning. Ah, that's a good question, Princess. I like the way you're thinking, because we're going to get there. We're going to get there. All right. We're going to get to the tan graph. We're going to start with the sine graph and the cos graph, and then we'll talk about what happens at the tan graph. And it's very interesting. I hope you guys will stick with me for this one. All right. We're going to get there. All right. Vukosi, just explain to me where to start explaining. Oh, there we go. I got lost if you explained to Narisha on the triangles. Oh, okay. So Vukosi, the only reason I was explaining the triangles is because Narisha was asking, why do we use r is equal to 1? Why do we choose the radius of every triangle to be 1? Because if we have a radius of 1, that's the easiest ratio that we can use. Okay. Because if my ratio is 1, I don't have to multiply it by anything. I can just keep it at 1. But if I need a bigger circle, I can just multiply 1 by whatever that is. And if I want a smaller circle, I can just divide 1 by whatever that value is. And that will give me the correct answer. Okay. Ah, all right. Okay, we're going to get there, Narisha. Okay, it's okay, Vukosi. All right, so when we look at these particular graphs, guys, I call these graphs the mother graphs. Okay, like I don't know if you guys have ever watched alien movies, but you know when they say like, take me to your mothership kind of vibe? This is basically what ma'am means when I say we're talking about the mother graph. Okay, so the mother graph is the main thing that we're always going to be looking at when we're trying to figure out the different ways that we're going to move the graphs around. But we're going to start with f of x is equal to sine x. So we're going to use normal signposts, okay, like 0 degrees, 90 degrees, 180, 270, and 360. I want everybody to have their calculator at the ready. You're going to start by putting in sine of 0 for me, sine of 0, sine of 90, sine of 180, sine of 270, and sine of 360. All right. And you're going to see that the values that we get here coincide very creepily to what's happened in this particular graph. Okay, I'll give you guys one more minute and then you'll see exactly what ma'am is talking about. All right, peeps, let's have a look here. Okay, so if we punch this into our calculators, sine of 0 is going to give me 0. And now you'll note that on my stretched out Cartesian plane, at 0, I've put in the point 0. At 0 degrees, I'm at 0, right? At sine of 90 gives me the value 1. So at 90 degrees, I go to the point 1 and I put a dot there. Right, sine of 180 will give me 0, and that puts the point there. Sine of 270 gives me -1, which is the point there. And sine of 360 gives me 0, which is the point there. So this would be 0, -1, and 0. Now, you would note that if you did every other degree in between, so if you decided to do sine of 89, it would give you a point right there. Sine of 80, it would give you a point there. Sine of 40, it would give you a point there. Sine of 30 would give us a half. Sine of 60, all of these would be put together and they would give us this kind of wave. Like that. And that is the sine graph. Now, to show you that your calculators always ensure that they give you an answer that is a ratio of 1, right? I want you guys to pick up your calculators and put in sine or shift sine, because we want the angle, put in shift sine of 1,4. Punch that into your calculator and tell me what it says. It says error. It says error, right? Because the original ratio of every single graph has a radius or a hypotenuse of 1. So we cannot get a value higher than 1. Same as if you look on our graph, if you look at this tan mother graph, the tan mother graph only goes up to 1 and goes down to -1. It doesn't cross any of those because the ratio is set in between them. So if we want anything bigger than that, then you put the number before the ratio. So you'd have to say 2 sine of 0,4. Then your calculator will find, shift sine. 2 shift sine of 0,4. Your calculator will find that answer, and then it will take that answer and multiply it by 2. Okay. All right. So because we've set that ratio or that radius to 1, that's what happens to that graph. All right. Okay. Let's look at the mother graph of cos. Okay. And again, we're going to do the exact same thing, guys. We're going to look for cos of 0, cos of 90 degrees, cos of 180, cos of 270, and cos of 360. And you'll see every single value you get will not exceed 1 or -1. The ratio has been, or the radius has been set to 1. Your values will not be greater than 1. The only exception is going to be tan, and I'm going to explain why. Okay. Okay. So if we punch this into a calculator, cos of 0 is 1, cos of 90 is 0, cos of 180 is -1, cos of 270 is 0, and cos of 360 is 1. So we've gone from there to -1, nothing further down than -1, 0, and back up to 1. And that's as far as we get, right? And that is the cos graph. Now, guys, when I say we need to understand what the mother graph looks like and what it does, I need us to commit it to memory. So you need to remember where the sign of 0 is sitting, where the sign of 90 is sitting, where sign of 180 is sitting. And I'm about to show you now. I'm about to show you. Okay, gift, I'm about to show you why. Okay. All right, so tan is a bit of a special character, okay, in that tan repeats itself every 180 degrees instead of 360. So instead of doing tan of 0, tan of 90, we're going to halve all of them. So we're going to look at tan of 0, tan of 45 degrees, tan of 90 degrees. There we go, Narisha, tan 135, and tan of 180. So let's punch these into a calculator. We're going to run into a problem. I want you guys to tell me where the problem is. Where do we run into an issue? At 90 degrees, correct. Right. Is everybody in agreement? Your calculator is giving you a maths error when you get to tan of 90. Right? We're going to find that tan of 0 is 0. Tan of 45 is 1. Tan of 90 is an error, or we're going to call it undefined. And I'm going to explain why it's undefined in just a second. Tan of 135 is -1, and tan of 180 takes us back to 0. So we've kind of done a full revolution from 0 back to 0. Okay, and it only takes 180 degrees for a full revolution of a tan graph. All right, let's go talk about why this is. Okay, so if my circle, I'm going to go back to the circle. If my circle has a radius of 1, right, what is this x coordinate over here? What's the x coordinate over there? Gift, I'm going to answer your question in just a second. Guys, the distance from here to here is 1. It's a radius. So my x value over here is going to be 1. Because it's an x-intercept, what is my y value going to be? Anybody? Yes, that's it, princess. Good. It's going to be 0, right? Good. Let's travel in this direction. The radius over here is still 1. But now this thing is lying on the y-intercept. So what is the coordinates over here? Correct. My x value is going to be, what's my x value there? It's a y-intercept. So my x value is going to be 0. Good. And my y value is going to be 1. Let's talk about this side over here. What are the coordinates on that side? Remember which side you are on. That's it, princess. Correct. My x value is going to be -1, and my y value will be 0. And down here, what would my values over here be? That's it. Okay, Theo, you're almost there. My x value is going to be 0, and my y value, because it's on the y-intercept, it's a y-intercept, my x value must be 0, and my y value is -1. All right, so let's think about this, guys. I know that SOHCAHTOA tells me that sine of theta is equal to opposite over hypotenuse, or on a Cartesian plane, it's going to be my y value over my radius. My cos of theta is going to be adjacent over hypotenuse, or my x value over the radius. What about tan? Tan of theta is equal to opposite over adjacent, or what over what? According to my y and my x and my r, what would tan be? Tan is equal to something over something. What are those two things? It's going to be opposite over adjacent. Opposite is my, correct. Opposite is my y value over my adjacent, which is my x value. So tan of theta is going to be the y value over the x value. Okay, thumbs up. Everybody okay with what ma'am's done there? Oh, Theo, nice one. Okay, cool stuff. So tan of theta will be y over x. Now, let's look on our circle, guys. Let's look on our circle. If I go to tan of 90 degrees, if I go to tan of 90 degrees, I know that tan at 90 degrees, at the point 90 degrees, my y value is 1 and my x value is 0. Put that in here. Tan of 90 would be y over x. That's going to be 1 over what? 1 over 0. What do we know about this? 1 over 0? That's undefined, correct. It's undefined. And that's why when we look at our tan graph, there's like a dotted line at 90 degrees, going down in this direction. Right, what do we call that? Do we remember what it's called from hyperbola and from the exponential graph? What do we call that dotted line that our graph can't cross? That's it. Yo, Narisha. Winning, 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 winning. That's it. Right. It's called an asymptote, right? Or as one of my boys at my school calls it, he called it an asthmatote. Like, you know, when somebody has asthma, he called it an asthmatote. And, you know, it's okay, as long as you know what it is and where to find it. Whatever you call it is whatever you call it. Okay. Yeah, so asthmatote, yes. Asymptotes, asthmatotes. Guys, it's fine. As long as you do it right and you get the marks. Oh, Gojo, I like that. Yeah, because, oh, Narisha, that is so smart. Can I please steal that? Can I please steal it? Okay, that is such a lovely reference. I'm going to steal it. Unfortunately, it is what it is. Okay, it's stolen. Thank you. Thank you. For those of you who are unaware, and I'm probably going to get in a lot of trouble for this, but I'm beyond caring because this is so cool. The character named Gojo in an anime called Jujutsu Kaisen, like, you can't touch him. Like, the closer you get to him, the more force there is. So punches never land. So if somebody tries to punch him, it sits right here next to him, like it can never touch him. So like an asymptote, like nobody can ever touch the asymptote because nobody can ever touch Gojo. How cool! That is the coolest thing. I love it. I love it so much. Ah, I see. Right, Asanda, it's so nice. It's so nice. I actually am quite a fan. All right, so that's cool. I'm gonna call it a Gojo because it's that cool. Thank you, Narisha. I must say, you guys are like by far some of the coolest people I've ever met. I never would have come up with half of the references that you guys come up with in these things. Oh, okay, let's focus, guys. Mother graphs. Mother graphs. Okay, so these three graphs are your sine, your cos, and your tan graphs. These are your mother graphs. Now, we're going to learn a couple of things before we continue. All right, first thing that we're going to learn about is the period of a graph. Right. And in order for me to explain the period of a graph, I need to explain to you guys something very simple. I need you guys to stick with me here. So if you're writing anything down, you don't have to write anything at the moment. I just need everybody to pay attention so that I hope everybody's understanding what we're saying. Okay. So if I look at, oh, look at what I'm doing. Okay. My OCD's kicked in, but it's fine. If I look at this, I know that if I start at 0 degrees, and I go all the way around my circle, how far have I made it? How far have I gone? If I go all the way around my circle, how many degrees? Good, I've gone 360, right? Now, If I wanted to go 720 degrees, where would I land? Right. If I went 720 degrees, I would just go all the way around and I would end up back at 360. Right, because 360 plus 360 will just bring me back around. It's okay. Yes, that's okay, princess. It's okay. This is where we make the mistakes. Right, I would land all the way around back at the same spot. What if I wanted to go 1080 degrees? 1080 degrees? That would just be me going around the circle again. That's 270. Again, that's 1080. How many times do you guys think I can do this? How many times do you think I can go around my circle? Okay, not not 3 times. I mean practically, logically, a lot, or let's be a little bit more mathematical about it. That's it, Theo. An infinite amount of times. I can do this infinity times. I can go again, around, and again, and again, and again. So technically, when I talk about my period, I'm talking about how long does it take me to go from one spot on my graph all the way around? How many degrees does it take for me to go around? So when they ask you for the period, what they're actually asking for is how long does it take to create one full revolution? Does it take to create one full graph, let's say, to create one full graph? All right. Now, in the case of my mother graphs for sine, I know that to make one full wave of sine, my period will be 360 degrees. All right. Tell me, guys, what is the period of my cos graph? How long will it take me to go all the way around on my cos graph? How long will it take me to go from 1, go down all the way back up to 1 again? That's it, Asanda, beautiful. That's it. Well done, Theo. 360 degrees. Now remember, tan is the exception. The period for tan, how long does it take us to do the same thing? That's it, Theo. It will only take us 180 before we start repeating the same thing again. Hello, Eric. Always lovely to have you. I think you may have answered me before. I just missed you, but I really did want to say hi. All right, so I know the period for each of these would be 360 because I'm going to end up in the same place. Let's prove this a little bit. All right, so everybody punch into your calculator sine of 30 degrees and tell me what your calculator says. It says 0.5 or 1/2, right? So what this tells us is that at the point 30 degrees over here, my graph touches the point 1/2, right there, 1/2, right? But because I know that my graph could go on forever, it's not just one place, it can keep going again and again and again. I can take this and I can draw a straight line from there right through like that. All right, we're going to pretend it's a straight line, guys. Don't judge me. Okay, there we go. It's somewhat straight, right? So I know that at 30 degrees, I've got 1/2. I want you guys to put sine of 150 degrees into your calculator as well. Put in sine of 150 degrees for me. It says 1/2 again, right? Yeah, it gives us 1/2 because they both cut the graph at the same place. But remember, guys, this graph could go one revolution, and then another revolution, and then another revolution. So 3 plus 360, 360, 360. So if I went here and I kept going on this graph, That's the same thing as 360 plus 30. So punch into your calculator, sine of 390 for me, and tell me what answer you get. It gives us a half again, right? And if I keep going, and I get to 510 degrees, punch in the sine of 510 degrees. It's going to give us a half again. So we can tell that our graph actually goes on forever and ever and ever and ever. And we can prove this by looking at our circle of radius 1, right? If I decide to make theta equal to 30 degrees, if this is 30 degrees, if I add a 4 revolution, if I add 360 to 30 degrees, that's 390 degrees. I should end up with the same answer because I'm going to end up in the same place. That means if I add another 360 degrees, I should end up with the same answer because I'm in the same place. And add another 360 and another 360 and another 60. And every single time I hit that spot plus 360, that that would give me a half. And Narisha, you completely threw me off. Oh, I can't believe you. Oh, stop it, you're too funny. Okay, all right. Thumbs up. Is everybody understand what Mem is saying? So basically, we are looking at the same graph again and again and again and again. We're just drawing one graph. And if we want many graphs, we can just add 360. Okay, but this goes in both directions, guys. It's not just add 360. We can also minus 360. We'd just be moving in the opposite direction. Okay, so if I had that, right? Oh, and all of a sudden it doesn't want to do the right things, Lord. When I needed that earlier, right? So I know that if I have my sine graph, there's 360, and I can draw another one that takes me to 720, right? Now I know that because this goes in that direction, my graph could also go in that direction. This is just going to be negative 360. And then I can draw another one, and that's just going to be negative 720, right? And all of them, if I had to draw a point at the halfway mark, right, at the point a half, if I had to draw everything at that point, this would be 30. If I took 30 and I minused 360, I'm going to end up at the same answer again. And if I take that same point there and I minus 360, I'm going to end up at the same answer again, because this graph is a perpetual graph. We're just drawing one revolution. All right, so it keeps going forever and ever in both directions. Right, same applies for cos. If you look at cos of 60 degrees, cos of 60 degrees is a half. I also know that if I take 60 degrees and I add 360, that would take me to 420. Cos of 420 would also give me a half. I also know that cos of 300 is a half. Cos of 300 is a half. If I take 300 and I add 360, same WhatsApp group. It's going to happen again and again and again and again. All right. Okay, let's look at the amplitude. Now, I need you guys to pay attention to the amplitude. I know it's going to be a bit confusing, but I need you guys to stick with me. The amplitude is how high up my graph goes from the origin. Okay, from the origin, and I'm going to explain in just a second. Okay. Okay, now I'm going to use the cos graph for this one instead of the sine graph, because I feel like I'm using the sine graph a little too much. Okay, if we look at our sine graph over here, I know that my whole graph spans from 1 to negative 1, right? But that's not the amplitude. The amplitude starts from the origin, from 0. So how high up does my graph go from the origin? How high up does it go? Just one unit. Right, correct, just one. So if I look at my cos graph, my sine graph, from the origin, 0, right? And don't think that the origin is always going to be 0, guys. Sometimes the origin is going to shift. Okay, and I'll explain that part when we get there. Okay, from the origin, the amplitude of my sine graph, so the amplitude is just 1, because from the origin to the highest point on my graph, that's 1. That means the amplitude of my cos graph, excuse me, guys, I think I'm getting the hiccups. The amplitude of my cos graph is 1. Now, let's look at the tan graph. What is the amplitude of my tan graph? Can it be 1, Theo? Can it? Is there a point where it turns and stops and comes back? Is there? No, correct. So okay, not undefined, but yes, there is no amplitude because this thing is competing, or my graph is competing with my asymptote. And they're both just going to keep going up, 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 up. They're going to get very, very close to each other. They'll never actually touch, but they'll keep going up, 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 all the way till infinity in both directions, because both my graphs are trying to get past, or my graph is trying to get past my asymptote, and it's never going to be able to do that. So for my tan graph has no amplitude. We say that it doesn't have an amplitude. And unfortunately not. Okay. Right. It has no amplitude. And lucky for us, I've never ever seen anybody in a test or an exam ask, what is the amplitude of a tan graph? Because there isn't one. What a pointless question. Okay. Pointless. So we hardly ever ask for the amplitude of a tan graph. It doesn't have one. Okay. So that is period and amplitude. Right. Now, the vertical shift we will get to. I'm going to do vertical shift in Wednesday's lesson. And then the only graph of the 3 graphs that has an asymptote is the tan graph. Tan only. Only tan has asymptotes, and tan has asymptotes at 90 degrees and at 270 degrees at these 2 points. No, Asanda, you won't. You won't have to. Okay. You will never be asked such a question. Most of the time, they'll ask you, determine the asymptotes of the graph. That's what they'll ask. Okay. And then you'll just say at 90 degrees and 270 degrees. I don't think it's that bad. I think it was pretty okay. Well, I think the explanation was pretty okay. I just need to double check with everyone on a scale of 1 to 10. Okay. Yeah, on a scale of 1 to 10, 1 being your ma'am, you spoke Greek the whole lesson. I didn't understand a single thing. And 10 being, I got you, ma'am. Next lesson, I'm going to be doing the things. Where are we sitting? How are we feeling about what we've just done? Okay. Princess is at a 9, Theo at a 10. I don't even know how to speak IT gift, so I'm not sure. I'm not sure how I got to be an IT technician when sometimes I can't even control my own headphones. So I don't know. I don't know. Okay, so if you're sitting at like a 5, I think it will take a little bit of time for me to actually show you what it looks like in a question, so that we're all comfortable with exactly what it is that we're doing. Okay, and if you're at a 9 or a 10, then everything that ma'am is going to do next is really going to help. Okay. I don't think so, guys. I don't speak that many languages. Guys, I only speak a few, just a few, not that many. Okay. All right. So I'm going to give you guys a tiny little preview of what we're going to actually be doing on Wednesday and how we're going to apply it. You don't have to write any of this down because I'm going to go through it in a little bit more detail when we get to it on Wednesday. Okay. So this is what the graphs are going to look like. Okay. So I want us to note something. Okay, just give me 1 second. I just want to steal this. Okay, I want us to have a look at something. Okay. This, don't stress it, don't sweat it, Narisha. This is the mother graph. The mother graph is f of x is equal to sine x, right? Now, I want you guys to look at the difference between the mother graph and the new graph that teacher Coco has given you. What have I added? What have I added? Which letters have I added? I've added an A, I've added a B. What else have I added? A Q, good. I've added an A, a B, and a Q. Now, let's go back to when we were doing things like hyperbolas and parabolas and exponentials. What does Q do? What does Q do in any of those graphs? It's a shift. Good. What kind of shift? Good. It's a vertical shift. Right. It's a vertical shift. Right. What did A do? What did the A value do? We said that if the A is positive, something happens. If the A is negative, something else happens. Right? If A is positive, my graph smiles or something along those lines. And if my A is negative, then my graph will frown or it will just invert. It had something to do with quadrants as well, Princess. Lovely. So all of those things are going to apply. Let's look at this middle part here. Okay, if we look at over here, I've added bx. What would I put here? Normally, if I just had sine of what would go here? A what? Is it an angle? Is it a ratio? What would we put here? It would have to be sine of It can't be a ratio. The answer I would get out is a ratio, but I would find sine of What was that thing that we would put in there? It's an angle. It would have to be an angle or theta, correct, Princess. So we'd say sine of theta. So we'd say sine of 30 or sine of 50 or sine of 90. All of that would go where x is, right? And we said that our graph has a period of 360. My graph goes from 0 to 360. Now, if I add in another friend b, what is that going to affect? It's going to affect my period. It's going to affect how many graphs I'm actually drawing. Okay, and we're going to talk about that in a little bit more detail on Wednesday. Okay, so this